by taking the Boyle's law, Charles' law, and what law? Avogadro law. Now, with the help of the synthesis of all these laws, we can derive ideal gas equation. What is that ideal gas equation? Ideal gas. Those gas which obeys Boyle's law, Charles' law, and Avogadro law. Those gases which obey Boyle's law, Charles' law, and Avogadro's law at all conditions of temperature, pressure, and concentration is called ideal gas. Practically no gas is ideal. All gases are real. So ideal gas exists only at low pressure and high temperature. When pressure going to increase and temperature going to decrease, the ideal gas changes into real behavior. So dear student, ideal gas equation is equal to PV equal to nRT. Right? What is P? P, you know it very well. It is what is that pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature in Kelvin. With the help of all these, finally we will get P1 V1 upon T1 equal to P2 V2 upon T2 for n mole of the gas, and R remains constant. So if we take these two, then PV upon T. Actually, PV upon T. For the initial condition, it is P1 V1 upon T1, initial pressure, initial volume, and initial temperature. And just like that, final pressure, final volume, and final temperature. So PV upon T can be accelerated as P1 V1 upon T1 equal to P2 V2 upon T2. How to derive this law? How to prove this law? We take the help of Boyle's, Charles, and Avogadro law. See here, just we go for the derivation of this law is here. Derivation of ideal gas equation according to Boyle's law. Volume is inversely proportional to pressure at constant temperature. According to Charles' law, volume is directly proportional to temperature at constant pressure. And according to Avogadro's law, volume is directly proportional to the number of moles, that is at constant pressure and temperature. This is taken as the equation third. So therefore, from the first, second, and third, we'll get here from equation first, second, and third, we get volume is inversely proportional to the pressure, directly proportional to the temperature, and directly proportional to the number of moles. So V is equal to proportionality change into R into 1 upon P into T into N, or P into V equal to what is that? nRT. What is N there? This P is the pressure, V is the volume, N is the number of moles, N mole of the gas, and R is the universal gas constant, and T is the temperature in Kelvin. So on the basis of that, if R constant and for N mole of the gas, so PV upon T let initial condition and the final condition P1 V1 upon T1 equal to P2 V2 upon T2. So you can frame it like P1 V1 T2 equal to P2 V2 T1. If you want to calculate the final volume in the numerical, so equation will be P1 V1 T2 upon P2 into T1. Is it clear to you, everybody? So if question comes in paper, derive ideal gas equation, then you take the help of Boyle's law, Charles law and Avogadro law. P1 V1 upon T1 equal to P2 V2 upon T2. Okay, now two things are important. Here you have to calculate the numerical value of R and unit of R. Right. So first we go for unit of R. Unit of R. We know that PV equal to, what is that? nRT. This is the ideal gas equation. Now R is the universal gas constant. So R is equal to PV upon NT. What is P? P stands for pressure, V stands for volume, N is the number of moles and temperature in Kelvin. So you know pressure is what actually force upon area, and this is the volume upon number of moles and temperature in Kelvin. Students, force upon area is the length cube and volume is the length square upon, this is the cube, and then moles and temperature in, what is that? Kelvin. So 3 and 2 cancelled out. So this is force, sorry, and that is, what is that? Area, volume is the length cube and this is the square. 2 or 3 cancelled out. Force into length, right? 3 and 2 cancelled out. It is the actually 2 and this is the 3. So force into length upon moles into Kelvin. That is the force into length is equal to joule, Kelvin inverse, what is that? Mole inverse. Force into length is equal to joule, work done. So R is equal to joule per Kelvin per mole. This is the unit of R. Now you go for the numerical value of R. See, numerical value of R. So dear students, the first point is when pressure is 1 atmosphere, volume is 22.4 liter and temperature is 273 Kelvin, then the unit of R is, pressure is the 1 atmosphere, volume is 22.4 liter and moles and temperature in Kelvin 273, then it is 0.0821 liter atmosphere, Kelvin inverse and mole inverse. Liter, atmosphere, Kelvin inverse and the mole inverse. But when pressure is taken in bar and volume is then 22.7 liter, then the value of R is 0.083 bar. Now liter, Kelvin inverse and what is that? Mole inverse. In CGS system, insidious 8.314 into 10 to the power 7 erg, right, degree, Kelvin inverse, mole inverse in SI unit. 1 joule is equal to 10 to the power 7 what? Erg. Therefore 8.314 joule Kelvin inverse mole inverse. So the way we'll remember the value of R at different parameters. This is what actually Boyle's law, Charles' law, Avogadro law, ideal gas equation, and the unit of R and the numerical value of R. And the last part for today's lecture is, you can see the Dalton's law of partial pressure. Dalton's law of partial pressure. Now, Dalton's law of partial pressure. According to this law, when two or more non-reacting gases are enclosed in a closed container, then the total pressure of the gas is equal to the sum of the partial pressure of gas. Let PA, PB and PC are the partial pressure of different gases, namely A, B and C, respectively. So let P is the total pressure. So apply the Dalton's law of partial pressure. Sum of the total pressure should be equal to the partial pressure of the different gases. So P total equal to PA plus PB plus PC and so on. This is Dalton's law of partial pressure. Now, what the application of this law? There are two applications. One is to calculate or to determine the aqueous tension. Second, the relation between mole fraction and partial pressure of the gas. So dear student, you write down first. You can see application of applications of Dalton's law of partial pressure. First application is to determine the aqueous tension when air is passed through the water molecule then some forces developed in the layer of water, which is called as aqueous tension. Like this, pressure of the moist air equal to pressure of the dry air minus pressure of the water vapor. Actually it is the aqueous tension. So pressure of the moist air equal to pressure of the dry air minus pressure of the aqueous tension. See, once you want to calculate the aqueous tension, then pressure of the moist air minus pressure of the what gas? Dry gas. It is one of the applications of the Dalton's law of partial pressure. Now next is the partial pressure and mole fraction of the gas. Another application is, last application is the to establish the relation between mole fraction and partial pressure. Let Na, Nb and Nc are the moles of the different gases A, B and C respectively. Let N is the total number of moles. Let Pa, Pb and Pc are the, what is that? Are the partial pressure of the different gases. Are the partial pressure of different gases A, B and C respectively. We know that PV equal to, what is that? nRT. So P is equal to nRT by V. This is the equation 1. For gas A, Pa is equal to nART upon V. This is the equation 2nd. Therefore divide equation 2nd by 1st. So whatever we are getting now, the relation actually is that, so divide 2nd by 1st, Pa upon P equal to nART upon V into V upon nRT. RT cancelled out, is cancelled out. So this is the Pa upon P equal to, what is that? Na. What is Na? Well, Na is the number of moles of, what is that? This is the Na RT upon V divided by V upon nRT, Na upon N. Right. So What is Na? Na is the number of moles of gas and N is the total number of, what is that? Moles. So what is the mole fraction of A equal to Na upon N? That is the mole fraction of A. So this can be put here in this form. Pa upon P equal to, this is the mole fraction. Na upon N is actually what? It is the mole fraction of A. What is that? So Pa equal to P into mole fraction of A. The way you can conclude that partial pressure of A is equal to the product of mole fraction and total pressure. So let you conclude it. Partial pressure of A equal to the products of what is that? Total pressure and what is that? Mole fraction. So dear students, today we want to recapitulate the lecture from the states of matter, that is the gaseous state, and I have explained you the Boyle's law, Charles' law, Avogadro law, and ideal gas equation, unit of R, numerical value of R, then how to derive the ideal gas equation, as well as we have explained Dalton's law of partial pressure, that is, and application of the, there are two applications of the Dalton's law of partial pressure. One is, you can see the relation between mole fraction and partial pressure, and other is how to calculate the aqueous tension of water. Thank you very much and have a nice day to all of you.